From the student perspective, do you know what's really nice? When you get asked an eigenvalue problem, there's really only one thing your professor can have you do. Give you a matrix, find the eigenvalues of it, and write them down. Works or it doesn't. So as long as you know the process, as long as you have a script that does it, that's a powerful tool to take with you. So we can do example problem 5-2. Show the eigenvalues of the following matrix are 3, negative 1, 1. The hardest part of this problem is entering in the matrix correctly once you have the script written down. Eigenvalues, very process driven. That's what makes it a useful tool. Also the fact that it comes from everywhere. So all eig of answer 3, negative 1, 1. We verified problem 5-2. Okay. We can even show the plot of what happened with those eigenvalues. Actually, there was a little bit of a numerical bouncing there. It's interesting. It converged, overshot a bit, and numerically just bounced back and forth. Notice that it's not smooth oscillations like you might get with a real dynamic system, but that's numeric convergence. Nifty. Let's take a look next at problem 5-4. A little bit easier. Let's give this a matrix name I. Problem 5-4 says the moment of inertia Ix, Iy, and the products of inertia Ixy and Iyx, which are equivalent, by the way, are given as such. They give some numbers. We'll punch those in a second. Find the principal moments of inertia. So you should have, definitely did in your structures class, but they call that solid mechanics, have calculated products of inertia as well as principal moments of inertia in two axes. What they may not have covered in those classes is that you can always convert in a rotated coordinate system what the principal moments of inertia are, so that you can diagonalize that matrix of information. So if you have Ixx equal to 5,286 as it is here, and you have an Ixy product of 2, 9, 14, so that's product of inertia. Of course, the Iyx product has to be exactly the same thing because of physics. And then Iyy is 4,331. That becomes your inertial matrix. Your diagonals, again, just like in the stress matrix, are your principals. Excuse me, not principals, they are your axial, kind of the repeated subscripts, so Ixx, Iyy, Izz, etc., etc. Actually, that's it. If you had inertia in time, then I think you're taking the wrong class. You're probably over there in some of that particle mechanics, crazy physics type studies. Anyway, off topic, back on subject. Stay on target. Let's do all eigenvalues of I. Oops. That's interesting. What caused that to break? See the matrix dimensions. Let's, why? What happened? Is it referencing something larger? So the fact this is a 2x2 is creating a problem? That's cool that it failed. Let's undo it. Let's clear variables. I will clear everything again to make sure this will work if you don't have any pre-existing variables. I still had stuff in there from previous examples we just run through. So let's see if we define this better again. Let me just type it back in since I nuked everything. 5286 2919. Is that right? Yes. No, 2914. 2914 and 4331. Okay. All eigenvalues of I. Maybe it's a problem with I. So let's do. Nope, it saved it. Let's change the name. Maybe there's a predefined I built in. No, interesting. Index exceeds matrix dimensions. Error in all eigenvalues, line 15. Well, let's find it. Oh, it's my own fault. Yeah. Well, it's bound to happen. My beautiful additions to the software created a problem. So let's see here. Update calculate. Of course, it works fine now. 7,761 is principal inertia number 1. 1,855 principal inertia number 2. And I do believe that has to equal the right answer. Let's verify. And yes, 7761. There's 1855. Sounds good.